Part 3 of cardiac. We move on here. This is where we stopped on the previous video talking about the autorhythmic cell and what the action potential looks like. It looks really different from what the skeletal muscle action potential looks like. So the first question I place to you here is where is the action potential coming from? And I'm saying it's an unstable membrane potential called a pacemaker potential. Let's look at why it's unstable. What is it about it? Let me get my pen out. Okay. You remember the action potential in skeletal muscle. I could draw it up here. And I'm just going to go up, and it's going to go back down again, and it's going to hyperpolarize and come back again. And we had a division here, didn't quite get it in the middle, so it looked pretty straight. I mean, mine doesn't. Now, the action potential in cardiac autorhythmic cells looks more like this. So look what happens. It's this slow depolarizing. We have it at minus 60 here, where it just slowly depolarizes, and then hits threshold. And then it kind of has an action potential, sort of more like the one that you remember, correct? So what is it about this pacemaker potential part? I'm going to change the color of my pen. So this pacemaker potential here is the term that I was using earlier, which is this unstable membrane potential. So it sits there and it will slowly depolarize. And it slowly depolarizes until it reaches its threshold. And then we think of it as the true action potential firing. This is pretty slow. It takes about 300 milliseconds. If you remember how long my AP took in muscle before, the contraction took 300 milliseconds or 400 milliseconds, but the actual action potential was only about 2 to 3 milliseconds. This is a lot slower. Do you notice? So sodium channels and calcium channels are going to open in a very similar way as to the regular AP that we were looking at earlier. Why is this happening? Well, we're going to look at the channels. Okay? So the slow depolarization is due to a sodium channel that is leaky, and it's letting sodium leak into the cell. So let's look. There is a slow depolarization happening, and which means that sodium is coming in. It leaks in, a little bit leaks in, and then when it hits this section here, now it's going to open a whole other set of channels that we haven't talked about before. It's a calcium channel, kind of like the one we talked about, insulin. Right? And it opens at that threshold, and that's what's going to cause the action potential. These are positive ions also. Notice? So calcium's going to come in. If it's positive, it's going to make this less negative, more and more positive. So that calcium channel is the one now that's sort of in charge of letting in the positive ions. That is the depolarization. Now, the repolarization that we think of as losing potassium, what happens there is that the calcium channels close and the potassium channels are going to open. So this part sort of looks familiar, right? Where potassium is going to leak out. If it leaks out of the cell, it's going to make that cell again become slightly more negative until it comes back down to the negative 60 that it was. So when this was first looked at by physiologists, they had no idea what was going on. And they thought, well, this is funny, like this is peculiar. And so they called them funny channels. So at first, these current channels are called IF, like for channel being a funny channel. Hence my little guy's laughing here. So it's these funny channels that are going to leak and then open a new calcium channel once that action potential, once that depolarization has reached around -40. Okay, so you're always going to draw your action potential coming from these pacemaker cells like this. A sort of flat line getting to a place, and then I'm going to have the regular action potential happening. And all of that's going to take about 800 milliseconds. So this is just expanded. So here are my funny channels. They're opening. And then some calcium channels are starting to open here, and then lots of them are opening on the rise. Okay? And the funny channels are limited sort of to this beginning. So these funny channels are going to close, and then this is going to take off when lots of calcium channels open, making it more positive. Calcium channels close up at the top, potassium channels open, and I lose positive, and regain my negative back again. And then my funny channels open all over again. Okay, I hope that's clear. So how is this controlled? Because this would give you an idea that that rhythm was always the same. You know, take a while, take a while, take a while, fire. Take a while, take a while, take a while, fire. But we know that our heart rhythms change, right? It accelerates or decelerates. So how does that work? Well, this is under the effect of the sympathetic and the parasympathetic nervous system. And what happens there is that the sympathetic stimulation and epinephrine depolarize the autorhythmic cells and can speed up that rate. So in red here, you're seeing instead of this slow, 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 I'm going to make it a whole lot faster happening here. So by releasing a certain neurotransmitter, I can speed up the leak. And by speeding up the leak, I reach threshold faster. If I reach threshold faster, and then I can fire more quickly. And the same goes for here. It's that slant here of that line. So if you're looking at that depolarization, it's going to happen way more quickly. So in comparison to the normal is in gray, and it would have taken a whole lot longer for enough of those funny channels to let that sodium leak in order for it to generate an action potential. So there you've just sped it up, right? You have 1, 2, 3, 4, 5 red action potentials for the 3 in gray. So it's the slope of this line, okay? It's the slope of the line that's changing. That sympathetic system can increase both the sodium flow and the calcium flow. Both of those are going to go more quickly. This slope here is also slightly more elevated than it is there. It's hard to see on this picture. And so you just sped it up. So now you had doom, 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 you know, lub dub, lub dub, lub dub is speeding up that heartbeat. And now let's look at it with a parasympathetic that's going to slow it down. The parasympathetic stimulation hyperpolarizes the membrane. And by hyperpolarizing the membrane, do you remember what that was before? We make it even more negative. And if we make it even more negative, then it's going to take longer to reach threshold. So more negative, and then my slant here, look at the slope of this line. It's going to take longer, and then fire, and then take longer, and then fire. So for every 2 blues that I have here, I have 3 of the normal ones. Okay, so parasympathetic system decreases calcium flow, increases the potassium flow, and it decreases the rate of depolarization. So now you have heart rate slowing back down again, right? And this is happening to you all day long. From the time that you wake up, you get out of bed, you then increase your heart rate just to, because you're upright now, and then you drop something and it startles you a little bit, your heart rate goes up, and then parasympathetic kicks in and it brings it back down again. So this is homeostasis. It's a play between sympathetic and parasympathetic. But this is how it's doing it. that was the action potential, what it looked like, right, of an autorhythmic cell in the heart, right? The pacemaker cell. Well, now I want to show you what it looks like when it's the contractile cell, the 99% of the cells that are in the heart. They're the ones that are going to actually form the contraction, and they need to have this action potential radiating through. So the action potential of the cardiac contractile cell involves 3 ions, and it doesn't look anything like the other 2, right? Look what happens here. It sort of shoots up, and then it has a plateau, and then it shoots back down again. So what's really different here, let me change the color of my pen. What's really different is this section, because the other is sort of similar. It goes up and then it goes back down again. But this section here is very different. So we can take this in steps. And these steps are all written out for you. And in the lecture, you can look at it in the lecture notes. But we're going to do it one step at a time. So let's take it from step 0. Step 0 has sodium channels or opening. And then if I bring sodium into the cell, does it make sense that it's going to become less negative? I hope you're with me. Then step 1 here is sodium channels close. So sodium channels are closed up at the peak. That's not that different from the other action potentials we spoke of. What happens next is, there's my plateau. Calcium channels, again, are going to open. And potassium channels, now we're going to distinguish 2 types. We're going to distinguish one type that is a fast channel and one that's a slow channel. So up at the top here at 2, we had calcium channels open, and those fast potassium channels are going to close. So none of that fast is happening. Nothing's happening with potassium. And therefore, I'm bringing in more positive, and I'm not losing positive yet. So if I keep bringing in more positive without losing any, it's going to flatten here on me, this mouse of mine. So I have this flat happening. Let's keep going to see what happens in 3. In 3 now, the calcium channels are going to close. So no more calcium coming in, and those slow potassium channels are going to open. So by opening, then I lose potassium again. By losing potassium, I will come back down to being negative. So really, what I want you to know, we can even not even think about these so much. Just know that if I have calcium channels here are open in 2, they close in 3, and those slowpoke potassium channels are the ones that are opening here, which is no different from that original action potential we looked at. 4 then, we go back down to the resting potential. Okay, so not that different, except for this funny plateau area up there, which makes it look really different. So why do we need that plateau? I'm telling you that the long plateau extends the refractory period, which means the time that it has to reset to fire again. So what we're looking at here is, in blue is the muscle contraction. Remember how long it took? These 300 milliseconds. That's how long it takes to be stimulated and then have a contraction and then have a relaxation, and then it's ready to do it again. Remember, we're talking about the heart. So it's contract, relax, right? Lub-dub. Now, if the action potential in these cells that are doing this, that are lub-dubbing, that are contract, relax, were very short, right? If you had an action potential here that was 2 milliseconds, and then you gave it another one, and then you gave it another one, and you gave it another one, what would happen to that cardiac muscle? Think about it. Like in skeletal muscle, it would begin to relax, but you'd give it another action potential, contract more. And you'd try and relax, and you'd give it another action potential, contract more. You don't want that to happen in the heart because you would create tetany. Remember tetanus? You would create tetanus in the heart, which means that instead of lub-dub, you would have lub, and it would stick there, right? And you would have this contraction that didn't release. Therefore, you have to have an action potential that lasts approximately the entire contraction and relaxation time of the actual muscle so that they're in sync. If they're in synchrony, then, right, on this side you're seeing the membrane potential, on this side you're seeing tension, then there is no way that you can overstimulate a heart muscle causing tetanus in the heart and therefore a heart attack. It'd be terrible. That would not work. To compare that of what happens in skeletal muscle, in blue again is the contraction, the peak, the relaxation of skeletal muscle. And what you can do is have the stimulus that's 2 milliseconds or 3, and you could stimulate again and again and again and again, and you would prevent that relaxation, and it would allow you to keep your muscle contracted. In skeletal muscle, you want that. You want to be able to hold a 10-pound weight and hold it for a while without dropping it. So we want that summation. Remember, we want summation to happen when it comes to skeletal muscle. We do not want that when it comes to heart. Reminder slide, skeletal muscle allows for summation and tetany, whereas we had one and another, and it builds upon itself and it never relaxes, and you obtain maximum tension. We don't want maximum tension in the heart. We want it to relax so that we get our lub-dub, lub-dub, lub-dub. This is certainly what you don't want, is tetany in the heart. This poor guy's looking at his hospital bill. Let's stop it there. My flag showed up. It's time to stop. Thanks.